In this video, we are going to talk about the last chapter in this course, chapter 15, which talks about nuclear magnetic resonance spectroscopy or NMR. So this is really important topic. Anytime that you make a new compound or you want to check the structure of compound that you have, you need to always utilize NMR. Because first of all, NMR is fairly easy to run, and also it will give us very important information that tells us a lot about the exact structure of the compound in the solution. So as I mentioned, NMR is the single most powerful method of gaining structural information. A lot of the times NMR is utilized with other spectroscopic techniques such as IR or mass spectroscopy. We are not going to talk about mass, but we already talked about IR in the previous videos. So to identify the exact structure of compound, there are a lot of NMRs that we can use. We can do hydrogen NMR, carbon NMR, fluorine NMR, phosphorus NMR, but in this course, we are going to focus on hydrogen and carbon because they are the atoms that can be found in almost every organic molecules, and we get the most useful information from them. So using these two types of NMR, hydrogen and carbon NMR, we can decide that which hydrogen is connected to which carbon or what hydrogens are adjacent to one another, which gives us a lot of good information about the structure of compound. In NMR, we are going to study the behavior of a specific nucleus, for example, nucleus of hydrogen or carbon in the presence of an external magnetic field. So we are not going to focus on the theory behind NMR, but something that we need to know about is that to have an active nucleus in NMR, the nucleus that we are studying should have a non-zero spin. So we are showing the spin of nucleus with I, and that spin should be non-zero. In order to have a non-zero spin, the nucleus should possess either odd mass number or odd atomic number, or both of these numbers should be odd. So for example, for hydrogen, we know that hydrogen has the atomic number of 1 and the mass number of 1. So both of these numbers are odd. Therefore, the spin for hydrogen is non-zero, and actually the spin for hydrogen is half. So for carbon, in general chemistry, you probably did the calculation for the carbon isotopes, carbon 12 and carbon 13. They are the isotopes of carbon. So carbon 12 is the most abundant by far. It's much more abundant than carbon 13. However, it's NMR inactive because carbon 12 has even mass number and even atomic number. So it has a zero spin. Now, in order to run carbon NMR, we are using carbon 13 isotope in NMR. So carbon 13 has the non-zero spin, but because it has very low abundance, it doesn't give us as much information as hydrogen would. However, it's still very useful, and it can give us very good information about the structure of compound. Now, in order to take an NMR spectrum of your sample, you need to prepare your sample. So there is a narrow glass tube that we use, which we call that NMR tube. So you don't need much of a sample to run NMR. You can even add as low as 10 milligram of your sample to the tube and dissolve it in NMR solvent to run it in the NMR instrument. Now, talking about solvent, the solvent that we use to dissolve the sample in, it should be deuterated solvent. So we don't use regular solvents in the lab because most of the solvents they have hydrogen in them, and we don't want the spectrum of solvent interfere with the spectrum of sample. So we are using a solvent that has all its hydrogens replaced with deuterium. Therefore, we don't see the hydrogen NMR of solvent in the spectrum. So the general deuterated solvent that we are using can be deuterated chloroform, deuterium oxide, which is actually deuterated water, and benzene D6. So this is the NMR instrument. This instrument is actually in JSP building in UK campus. You can see a ladder besides it. That's because you actually need to insert your sample to the instrument from the top, and not every person can reach the top easily. So we use this ladder. Now this instrument gives us the FID, free induction decay, and then with the use of computer and mathematical techniques we can transfer the FID to the NMR spectrum. So we can read through this spectrum, and actually this spectrum is much easier to interpret than the FID. Now let's talk about NMR time scale. So if you remember, we talked about chair conformation and the chair flip in cyclohexanes. So the chair flip is happening very quickly at room temperature. Now if you want to run the NMR of your cyclohexane sample at room temperature, NMR cannot differentiate between the hydrogen in equatorial and in axial position. So we are going to see a single peak for both of these hydrogens. And basically what we see is a time average picture of the molecule in NMR. Now if we run NMR at low temperature instead of room temperature, so if you have a liquid and you have your sample in it and you decrease the temperature, this will immobilize the molecule and makes the chair flip to happen much slower. And that helps the hydrogen NMR to distinguish between the chair conformations and the axial and equatorial positions. So for example, if you run NMR at high temperature, for cyclohexane, the NMR will see a single peak for both equatorial hydrogen and axial hydrogen. Now, as we decrease the temperature, the chair flip is happening slower and slower. Therefore, it gives time to the instrument to distinguish between the hydrogen equatorial and hydrogen axial, and we are going to see two separate peaks for them at very low temperature. Now, when we have the hydrogen NMR spectrum, there are four characteristics that we are going to look at in the spectrum. So the first one is the number of signals. So for example, in this spectrum, we have 1, 2, 3, 4 different signals, and it indicates the number of different protons that are present in the molecule. The second characteristic is the signal location, so which shows the position of each signal in the hydrogen NMR. So here we are looking at ppm. So in the x-axis we have the ppm value, which usually starts from 0 to 12. For example, this signal appears at 2.4 ppm, which shows the location of that specific signal. The third one is the signal area or the integration value. So the integration shows us the area under each peak. So for example, the area under this peak is shown as this integration. And basically this indicates the number of hydrogen atoms that are giving rise to each signal. And the fourth characteristic is the shape. So if you look at the shape of this specific signal, it's a triplet. It has 1, 2, 3 peaks in that signal, so we call that a triplet, and it talks about splitting patterns in the hydrogen NMR. Now we are going to look at all of these characteristics in the following slides and how these characteristics can help us to identify the structure of the molecule. So let's look at the first characteristic, which is the number of signals. So this indicates the number of different kinds of protons that are present in the molecule, or basically the number of protons that have different chemical environment. Now, protons that are chemically equivalent, or basically they have same chemical environment, they show only one signal in hydrogen NMR. And two protons are chemically equivalent if they can be interchanged using a rotation axis or a plane of reflection. If they cannot interchange using these symmetry operations, they aren't chemically equivalent and they show different signals in hydrogen NMR. Now, based on that, we can have different types of protons. We can have homotopic, enantiotopic, or diastereotopic protons. Now, to explain these terms, let's look at the following examples. So let's say we have an ethane molecule and we want to know what's the relationship between these two protons. So this proton and this proton. So what we can do here, we can draw a ethane molecule again, and then replace each of these protons with another atom such as deuterium. We call this a replacement test. So what we can do, we can take one of these protons in wedge and convert it to the deuterium, and take the proton in dash and convert it to deuterium. Now we need to examine the relationship between these two molecules. So we can see this carbon here, even with deuterium there is not a chiral carbon. So we didn't form a chiral carbon here. Now these molecules are actually the same molecules, and we can convert them to one another if we rotate one of them, for example this one, along the horizontal axis that passes through the molecule. So if you imagine there is an axis that passes here, rotation around this can convert this structure to this one. Basically, they are different conformations of the same molecule. So these two molecules are identical. Therefore, these two protons are homotopic. Now, if we look at butane molecule, again, we want to know what's the relationship between these two protons. So we are going to do the exact same thing. We are going to do the replacement test. So we are going to replace each proton with deuterium. Now after doing this, we see that this carbon is a chiral carbon. So we are generating a chiral center. Now if we examine the relationship between these two molecules, they are actually enantiomers. So we are generating a chiral center with opposite configuration. Therefore, these two molecules are enantiomers to one another, which cause these two protons to be enantiotopic protons. Now let's look at this compound right here. So we are actually replacing one of the hydrogens in butane with OH. Now we want to know what's the relationship between these two hydrogens now. So this hydrogen and this hydrogen. So what we are going to do again is the replacement test. So we are going to replace each hydrogens with deuterium. So the wedge hydrogen with deuterium and the dash hydrogen with deuterium. Now we need to examine the relationship between these two structures. So replacement of deuterium causes formation of the chirality center here. So we are generating a chiral center, and it has different configuration in both of these structures. Now something that we need to be very careful here is that there is a pre-existing chiral center in this molecule. So this center right here is a chiral center, and we didn't touch this chiral center, so the configuration in this chiral center should be the same in both of these structures. However, the configuration of the generated chiral center should be opposite in both of these structures. And if you remember, when we have two molecules that they have the same configuration in one of the centers, chiral centers, and they have opposite the configuration in the next chiral center, they are diastereomers. So these two protons should be diastereotopic. So homotopic or enantiotopic protons give you one signal in hydrogen NMR. But diastereotopic protons gives you different signals in hydrogen NMR. So diastereotopic are not identical. Now let's look at a few more examples and decide what's the relationship between the hydrogens in the molecules below. So let's look at the first molecule. We can do the replacement test. So I can replace the top hydrogen with deuterium. and in the other structure I can replace the bottom hydrogen with deuterium. Now I need to examine the relationship between these two structures. First of all, by replacement, I didn't generate a chiral center, so they cannot be enantiotopic or diastereotopic. And of course, when it is not enantiotopic and diastereotopic, they are homotopic. However, there is a rotation axis right here that can convert these two molecules to one another. So these two protons are homotopic. Now let's look at the next structure. Again, we can do replacement test. So I replace each proton with deuterium. Now I need to examine the relationship between these two structures. So first of all, replacement of deuterium forms a chiral center in both of these structures, and there is no pre-existing chiral center in the molecule, so these two structures are basically enantiomers, and the protons, these two protons, should be enantiotopic protons. Now let's look at the last structure. Again, we can do replacement test. So again, doing the replacement test, I formed a chiral carbon, chiral center right here. Now there is no other chiral centers in the molecule. So again, these two structures are enantiomers, and the relationship between these two protons is enantiotopic. So as I mentioned, diastereotopic protons show different signals in hydrogen NMR. Now, if you look at this structure, we want to know what's the relationship between these two protons. So again, we can do replacement test here. You can try it at home. Now, by doing replacement test, we are going to form a chiral center right here. And also there is a pre-existing chiral center in this molecule, so these two protons are diastereotopic. And this actually makes sense because this hydrogen in wedge is closer to the OH in wedge comparing to the hydrogen in dash. So therefore they have two different chemical environments. They show different peaks in hydrogen NMR. So the only time that you should think of diastereotopic protons is when we have a chirality center, pre-existing chirality center in the molecules such as this. And this can only happen to CH2 protons. With CH3, this does not happen. So the CH3s here, all the hydrogens are identical. However, these two hydrogens in CH2, they are diastereotopic and they show two different signals in hydrogen NMR. Now let's look at these two examples and decide what's the relationship between these two protons and these two protons. So let's focus on the first one. We can do deuterium replacement or replacement test. By doing that, we are going to generate a chiral center right here. Now there is a pre-existing chiral center in this molecule, therefore these two protons are diastereotopic. And diastereotopic protons, they are not equivalent. So they show two different signals in hydrogen NMR. Now let's look at these two protons. Again, we can do deuterium test or replacement test. So by doing that, we are not forming a chiral center because these two parts are identical. Since we are not generating a chiral center, these two protons are homotopic. And homotopic protons are equivalent, and they show one signal in hydrogen NMR. So basically there are some shortcuts that can help us with identifying the number of signals. So if there is no chirality center in the molecule, the two protons are either homotopic or enantiotopic. So we see only one signal for them. But if there is one chirality center in the molecule, the two protons are not equivalent, they are diastereotopic, and we see separate signals for them. In most cases, the three protons on methyl group are going to be equivalent. So we see one signal for all of the protons in methyl. And also if we have plane of symmetry in the molecule, the protons are equivalent. Now let's look at a few examples. So in order to count the number of signals in NMR, we need to know how to identify protons that are chemically equivalent. So basically these three protons, they are the same. So we are going to see one signal in NMR. These two protons are the same. They are going to give one signal. These two are the same. They are going to give one signal. And these three are the same. They are going to give one signal. So we have a total of 4 signals here, even though we have more hydrogens than 4 in this compound. So we have 10 hydrogens, but there is only going to be 4 signals in hydrogen NMR. Now sometimes you can have a compound such as this. So if we go through the same analysis, what we find is that these 2 hydrogens are going to be the same, and these 3 hydrogens are going to be the same. Now here there is a symmetry in the molecule, so there is a plane of symmetry in this molecule. Therefore, what we find is that these 2 protons are the same as these 2 protons. So we are going to see only one signal for these 4 protons. Also, these 3 hydrogens are going to be the same as these 3 hydrogens because we have symmetry in the molecules, so we are going to see only one signal for all of these 6 hydrogens. So overall this compound is going to show 2 signals in hydrogen NMR. Now let's look at another molecule. So this is a cyclohexane. Now cyclohexane has 12 hydrogens. These 2 hydrogens, these 2 hydrogens, these 2 hydrogens, all the hydrogens around the ring they are all equivalent because there is a plane of symmetry here, here, and here, which makes all of these hydrogens to be identical. So we are going to see only one signal for cyclohexane. So these are the symmetries in cyclohexane. So for all the corners and all the edges, you can draw a symmetry. So we are going to see one signal for cyclohexane. Now let's look at another molecule, which we call that para-dimethylbenzene. So here we've got 3 hydrogens, and here we have 3 hydrogens. So these 3 hydrogens are going to be the same as these 3 hydrogens because there is a plane of symmetry here. Now on a ring we have 4 hydrogens. So there is a symmetry like this here and a symmetry like this here, which makes these 2 protons the same and these 2 protons the same. So basically what we can say, all of these 4 protons are the same as each other. So we see one signal for all of these hydrogens on a ring. So these 4 are going to show one signal, and these methyls are going to show another signal. So we are going to see overall 2 signals for this molecule in hydrogen NMR. So let's look at more practice problems. In the first structure right here, so there is a chlorine in one side of the molecule and bromine in another side. Therefore, none of these 4 hydrogens are going to be equivalent. So this hydrogen is closer to chlorine and bromine. This one is closer to chlorine and 1 hydrogen. This hydrogen is closer to 2 hydrogens, and this hydrogen is closer to bromine and 1 hydrogen. So as you can see, all of them have different chemical environment. Therefore, they are not the same, they are not identical, and we are going to see 4 different signals in hydrogen NMR. Now, if I replace chlorine with bromine here, now replacing chlorine with bromine, so this part of the molecule would be exact the same as this part, meaning that there is a symmetry in the molecule right here. So I'm gonna see one signal for this proton, one signal for this one, and these 2 hydrogens are gonna be the same. So I will see one signal for both of them. So overall, I'm gonna see 3 signals in this molecule. Now let's look at another example. So in this molecule, we have a chirality center. So we already talked about that. CH3 are going to show one signal, so all of these hydrogens are equivalent. So we see one signal for this CH3. Now all of these 3 hydrogens are also the same, so we are going to see one signal for them as well. Now these 2 CH3s are not the same because this one is closer to bromine comparing to the other one. Now since we have a chirality center, for CH2s, hydrogens on CH2s are not identical. So they are not equivalent, therefore we are going to see signal for all of them. So we have one CH2 here and one CH2 here. So overall we are going to see 6 signals in hydrogen NMR for this compound.